just a one barrier, but I can go more general actually. So imagine I have a Borel set. You can see that a Borel set in R. So if I have a Borel set in R, could be interval, could be singletons, could be anything. You know that it's a pretty almost all known things that we usually deal with are Borel sets. Right? So it could be anything. And imagine I have a process X. Goes facing like that. And I'm defining a random variable tau b in this manner. Then tau b, whenever operated onto a trajectory, okay, onto an omega, okay, it's going to be. So how should I write the first hitting time? So I have a process X and it hits a barrier. So how should I write it? So it should be the first instance. So the infimum, okay, of the times. So if I have times, I must write n bigger than or equal. Infimum of the instant. The first instant, such that this process xn, obviously evaluated at omega, so it's just one trajectory,
is equal to the equivalent.
not equal to but belongs to the b. So if you want equality, just take b to be a singleton n or something like that, or some k actually.
So the barrier is the Borel set.
Yes. Okay. Vary with the Borel set. So in other words,
Interval of the set.
so it could be interval, it could be a singleton, it could be anything actually.
Set of some singletons.
So इसमें भी underline स्पेस हमारी R है या कोई और X है, मतलब जो ये random variable defined है, नहीं D, ठीक है.
Is it right? So I'm defining the time tau sub p and relevant to omega. So it's the first instant such that this process enters into this ball actually. So the more appropriate picture would be maybe you have a ball or interval or whatever, and this process kind of enters first time and could leave the ball as well. But I'm interested in the first instant when it enters into the ball or it hits your required barrier. Question: is this what do you call stopping time? That's what we like. Whether it's a stopping time or not. Does it satisfy the definition of the stopping time? Okay. By the way, this time is called a first hitting time. Okay. It's a first hitting time. And it makes sense to give it a name that, okay, this stochastic process is, so tau b is the first instant that the stochastic process enters into the B, or Borel set, or barrier, or anything. By the way, what is the meaning of xn of omega? So when I'm writing xn, you have to keep one thing in head. So when I'm writing an abstract process xn, I'm not talking about one such path. So I have what you call a zillions of paths basically, which goes beyond. So I'm saying that if you fix omega, then the process is going to follow one such path. So if I'm writing xn in general, I'm not talking about this example from this. So if I'm writing xn, it's a process which can take any path. But when I'm writing xn of omega, at least I'm talking about a one concrete path actually, out of many paths. Okay, and I'm saying that you give me an omega, and consider a path corresponding to this omega, and you are interested in that, okay, corresponding to this omega, when this path is going to enter into the Borel set. And the moment it is going to enter into the Borel set, it's a stopping time. Okay. By the way, this also could be infinity actually. In other words, it can also happen that the process never enters into the Borel set actually. So in that case, we will just put tau to be infinity. Now consider the proof that y for n bigger than or equal to 0, consider the omegas for which tau b is less than or equal to. In other words, less than or equal. I need to show that this belongs to. So if this is the case, I can say, what does this mean? This means that the process has entered into the ball, okay, at any instant before the n actually are equal to it. So at what time it can enter? 0, 1, 2, up to n. So thus I can write this as a union of k equal, for example, 0 to n, okay, such that
Tau b.
x of xk, I should say xk, enter into the ball. Okay. What do you mean by that? What do I mean by that? Can you see the interpretation of it? You can't see the interpretation. So, I'm saying if the time when the process entered into the Borel set is less than or equal to n, what does it mean? It means from 0 up to the time n, at any instant, the ball has entered, the process has entered into the ball. So that's what I'm saying. Okay, maybe x naught, the first instant in the process, started and it entered into the ball actually. In the first instant. Maybe it started and
x2.
X2
say.
Yes, to see more explicitly, union of k equal to 0 to n, and you write tau b equal to
Okay.
tau b equal to. Tau b equal to.
Say.
But what is the meaning of tau b equal to k? What is the meaning of tau b equal to k? It means that a time k, the process entered into the ball. Okay. Here's the question. Does this guy belongs to Fn? No, so yes, why not? Okay. No, because filtration contains all information about the process X actually. I should say that's an adapted process. Okay? That's an adapted process. So if it's an adapted process, what does it mean? So the filtration, Fn knows everything about the process X, okay, up to the time n. So I would say that X naught belongs to B is going to belong where? Is an F naught, but that F naught is a part of
F1.
F1 and hence Fn actually. So that's where is going to be the X2 belongs to B? Okay. So where can I find the information about X2? So X2 is F2 measurable. So if it is F2 measurable, This is nothing, this is just x2 inverse of the Borel set. So this belongs to the F2 by definition. Okay. Belongs to the F2 by definition. So you can see that all of these guys are going to belong to Fn. Okay. At the end, and that's it. This means that this time, this first entering time is stochastic